Hi, it's Moser with a quick tutorial on Lewis structures of weirdos, not for weirdos. That's a different video. So after watching this video, you should be able to construct a Lewis structure for any compound, including those which violate the octet rule in one way or another. Now, what you already need to know is how to draw Lewis structures for neutral octet conformers, how to draw Lewis structures for octet-conforming polyatomic ions, as well as how to draw Lewis structures for octet-conforming molecules and polyatomic ions which require resonance. Whew, that's a lot of stuff. Okay, let's go. So there are three categories of weirdos when we talk about Lewis structures. There are compounds which do expanded valence bonding. There are compounds which don't have complete octets. And then there are free radicals. So let's start with expanded valence. Let's start with this, SF6, sulfur hexafluoride. It's a lovely little compound. You remember sulfur, fluorine, 6 valence electrons, 7 valent electrons. What could possibly go wrong? Except you already know everything's going to go wrong, but, well, anyway. So we're going to start off by just trying the Gooch math to prove that it doesn't work. So we'll figure out our valence, we'll figure out our octet, and we'll subtract the 2. And this says we would have 8 bonds, but we only have 6 things hooked to sulfur. What would that look like? Not good? That's what it would look like. So obviously that's not a possibility. Well, what we end up with is something that looks like this. But how did we end up with that? Well, that's the question. Let's do this together. Since we know that the Gooch math doesn't work, we're going to ignore this part. We can tell that this doesn't conform to the expectations we have for an octet-conforming compound. But it's useful to keep in mind, well, no, that's not going to work either. Okay, let's get rid of that. So we know we have 1 sulfur and 6 fluorides. That's a good start. Now, what goes in the center of this compound? We know that it's carbon if it's there. We don't have carbon. Or the least electronegative thing we've got. That would be sulfur. So I'm going to place sulfur firmly in the middle of my drawing. Now I have 6 fluorine atoms to attach to this sulfur. I don't have a whole lot of choices. 1, 2, 3, 4, 5, 6. Hey, look at that. Held together by single bonds, I have 1 sulfur and 6 fluorine. Remember that fluorine is incredibly electronegative, and it came in with 7 valence electrons. It's not going to give any of those up, so I want to make sure I show all those unshared pairs. And believe it or not, what we have here is the structure of sulfur hexafluoride. Now, why does this happen? Well, you have to be careful. This sort of thing can only happen when 2 things are true. 1, you're dealing with elements in the 3rd period or below. You're going to understand why in a second. And 2, those elements in the 3rd period or below, when your central atom is in the 3rd period or below, those are bonding with something that's incredibly electronegative. Occasionally oxygen, but more commonly a halogen. So why does it matter that the central atom is in the 3rd period or below? Because what's actually happening here is that the fluorine is so strongly able to attract electrons that d orbitals in this sulfur are actually getting involved in the bonding process. Let's go back and look at sulfur's electron configuration. I'm sorry, I misspoke. It's not electrons in their d subshells, but they have d subshells. And so we have space up on that 3rd occupied main energy level for fluorine to pull things from inner shell electrons out closer to a point where they can end up participating in bonding. So again, we only see expanded valence bonding with elements that are in the 3rd period or below as the central atom. And we only really see it happening when things in that 3rd period or below are bonding with some of the most electronegative elements there are. Okay, you will see some of these, and it's useless to try to do the Gooch math. In place of the Gooch math, you just want to write non-conformer or expanded valence bonding. If you want to try to do the Gooch math like this to show that it doesn't work, you're welcome to. Let's move on to our second category of weirdos. incomplete octet compounds. This little beauty is boron trichloride. So remember, boron has 5 protons. It's in group 13, and there is chlorine, one of our favorite halogens. So I've already told you the Gooch math isn't going to work, but let's go ahead and try it to show that. Okay, I have these compounds. I figure out my valence. I figure out my octet. It shows that I should have 4 bonds. Well, wait a minute. What am I putting on the 4th bond? It's only bonded to 3 things. That doesn't make any sense. You're right. But if we hook the boron up to 3 chlorines, and remember we have to add their unshared electrons, everybody looks more or less okay. We tend to see this sort of incomplete octet bonding with boron. And it's really the only thing we see it with. But whenever we see a compound that has boron in it and the Gooch math doesn't work, we start to suspect that it's probably incomplete octet. How would you go about figuring this out, knowing that the math doesn't work? Well, again, we take the numbers of things we have. We know boron has to be in the middle because it's the least electronegative element in this grouping. And I have 3 chlorines, so I'm just going to try grouping them around with single bonds. I don't want to forget the unshared pairs on my chlorines. Chlorine would never give up its unshared electrons. It's far too electronegative for that. And this is the likely structure. Now, we can do some testing to determine if this is the actual structure or not, but that's a little bit beyond the scope of a high school general chemistry class. So, we kind of accept this. If you're interested in learning how to prove structures as most likely or least likely using formal charges, ask me. Maybe I'll make a tutorial on that. Now let's talk about the last category of weirdo, and frankly, the one you're never going to see in this class. Free radicals! It sounds exciting. It sounds like revolution and intrigue and uprising. It's not. Free radicals are compounds like nitrogen monoxide. It's 1 nitrogen double bonded to 1 oxygen, and free radicals have a single lone unpaired electron. They're desperately seeking electrons, so they tend to not stay in this form for very long, but to either steal an electron from someplace else, becoming a polyatomic ion, or bonding with another element, another atom, or another group of atoms. So again, you should never see a problem in the scope of this class where you have a lone unpaired electron, like this one, but you should be aware that they do exist. If you're going on in chemistry, you may see them, and you may learn how to figure out the most likely structure for a free radical compound. Again, that would be using formal charges. All right, fantastic. Keep going. On to molecular geometry for you.